So this whole Alice project is about cooling down atoms.
Mm-hmm.
So now I'm not a physicist, so I'm not an expert on that. So maybe you can just briefly explain what's the physics behind this? What's actually going on in the lab?
Temperature is directly related to some velocity. So if you imagine the air as a gas here in the room, it's quite warm and it's these air molecules bouncing around. They are really fast, and that's what makes things warm, basically. That what we can relate to temperature. And so if we cool down atoms, it basically means they get slower and slower and slower until they eventually stand still. So
it will also become easier to control then if they're very cold?
They are much more easy to control. We can pick up single atoms, can move them around to a different place. We can build structures with these atoms if we want. And another advantage of when we cool down atoms, there's also some quantum mechanical feature with it. So what maybe maybe you heard it, there's something called Heisenberg's uncertainty relation, which means basically easily saying you can't tell of an object, you can't tell at the same time the exact position or the exact velocity, either or.
Yeah.
So now the atoms get slower and slower and stand still. So you know kind of their velocity very, very precisely, which at the same time means that the position gets very undefined. So the atoms they are not described as a single particle anymore. They are described like as a wave. And if you play quantum moves, it's actually this wave that you see there. That's this wave behavior of what the atoms do. And if you have a lot of atoms together, then these waves start to overlap and kind of form a big wave. Then you create a Bose-Einstein condensate, and that's what we do in the lab basically. And that then forms as a tool for our further quantum simulation, because then we can really build super clean structures with these atoms, super clean artificial crystals, for instance. And they are super clean because everything is cold and everything is as it's supposed to be. If you have a real crystal in nature that has always some defects or whatever, we can build super clean crystals, super clean systems. And that is very important if you want to understand these systems on a microscopic level.
So how do you then do that? How do you create this Bose-Einstein condensate?
Basically, multiple steps involved, and we for in the Alice challenge we only picked the last step to cool the atoms down finally to the very cold temperatures, and that's happening basically in kind of we have the atoms trapped in a magnetic field and in a combination of magnetic fields and laser beams, and you can imagine it more or less like in a cup. So the atoms are in a magnetic cup. And then we have to transfer this magnetic cup into a cup made of laser beams, where then the atoms are also held. So I have to transfer these atoms from one cup to the other, from magnetic field cup to a laser cup, so to say. And then I have to deform this cup in the right way that always the hottest atoms can escape. It's like a hot cup of coffee, like you see the steam coming up, like evaporating, and it's this so-called evaporative cooling. So the hottest atoms can escape, the cold atoms remain, then we deform the cup in the right way that always the hottest atoms can escape, and the remaining atoms get colder and colder and colder. And if you do that in the right way, you don't spill away so many atoms. So if you do it the wrong way, then a lot of atoms get lost and you just end up with no atoms or very few cold atoms. But if you do it in the right way, then you get very efficient in this cooling process and you can get a lot of atoms, like a lot of cold atoms. And exactly that process we try to optimize, and with the help of the citizen scientists.
Yeah, so the citizen scientists are really manipulating the magnetic cup and the laser cup. Yes, exactly.
So the people had these three curves in the Alice challenge interface, which represent the magnetic field and the two laser beams, or the intensity of the two laser beams. So they could deform this cup as they wanted. They could make it from a magnetic cup to a laser cup and vice versa, and play around and investigate all these different possibilities.
I'm not a physicist, so this sounds complicated. You have laser beams and magnetic fields. Why go to citizen scientists who are not, I mean, you're the physics expert.
Yes.
So why do we go to the citizen scientists?
I mean, that's I guess one of one of our things that we do in ScienceAtHome that we have also already other good experiences with citizen science experiments, and also outside of ScienceAtHome. I mean, there are a lot of complex problems that were solved together with the citizens. And we started, that was 2 years ago, we started with a collaboration with some theorists to investigate how are these, well, we know that there are some solutions how we produce cold cloud of atoms. We know that this is a complex landscape, so if you imagine it as a landscape, there are some certain spaces where we can make atoms cold, and if these positions in this landscape are basically corresponding to how these traps are formed or these cups are formed. And we don't know exactly how this landscape looks, so we know that there are certain peaks where we can produce cold atoms, but we don't know the whole landscape, and it's huge. And we needed to find ways to search in this landscape. And it turned out that citizen scientists, if they get the right interface, or if they get the right tool to do things, to solve problems, that they are really efficient, which we saw also in the quantum moves game, and which we thought we could maybe also see with our particular problem here.
Yeah, and I guess that's also then where my social science interest then comes in.
Exactly. So
that my interest is here, as you said, we know that citizen scientists in former projects have turned out to be very good at solving these problems. And then my question is, well, how come? Why is it that they can be so good at solving this? And that's a big question in social science, is that how can we optimize problem solving? We solve problems all the time in business, when you're a student in school, when you're teaching, when you're trying to explain things. We always try to solve a problem. And here we saw an opportunity to, in a controlled environment, have people trying to solve a problem that is really, really difficult, as you say. There are millions of different ways that you can try to approach this problem, while the studies that we usually do in the lab.
Yes, exactly. What are you usually doing?
Yeah, so in the lab we would maybe have, we have a social science lab. We might have 20 people showing up, and they get exposed to some problem on a computer, and they click on stuff, and then we learn about how people solve problems. But these problems are usually very, very simple. It's like literally clicking on this image or clicking on that image.
So you have two images, which...
Yeah, and then you either do the same or you do something different. So you have like really simple and artificial problems. So when I then look at what people have done, I can't use that in the real world. I mean, people click more on this than on something else. That's not gonna help me. I want to find out how real problem solving goes on. And here I had an opportunity to look at a very, very high dimensional, very difficult, complicated problem, but still in a controlled way.
Is there any hypothesis why people can, successfully optimize in such a setting?
People, and we've shown that in many other connections as well, that people have a tendency to do what we call adaptive search. So if you perform really well, so imagine that you are playing this game and you score a really good, you cool down a lot of atoms, let's say 1.5 million, and then in your next attempt you will do a small modification. That's what our results show. That people who do well, they have a tendency to then be local, a bit conservative, of saying, I'm apparently in a good place here, let me just do some small modifications. While in contrast, if you're doing really poorly, let's say you were like second last on this leaderboard and then you were just like really not cooling down any atoms, you would in the next attempt do a big change. You would try out something dramatically different. You can sort of relate this to if you're cooking something, you have a recipe and you are following it and it turns out that it tasted great. You had guests over and they're all really fond of it. The next time you might do some small tweaks because you still think you can optimize and perfect it, but it's going to be small adaptations. You're not going to like really fundamentally do something completely different. While in contrast, if you had guests over and they were polite, but they actually should have said that this was really, really bad, well, the next time you're not going to do a small tweak because apparently you're just doing something completely different. So people, we adjust and adapt our behavior based on feedback. And that's in the game, in cooking, and if you're a business, it's a very sort of broad finding. But what that actually then leads to is when you have a collective of people where some optimize on the current best and others try out completely new things, you have a very efficient collective search algorithm because you're both optimizing on the current best and you're trying out new things. So without every single individual knowing it, we just have these tendencies of adapting our behavior that this leads to a very effective search algorithm. And that's really that's sort of one element of the main finding that we have, is that how individuals adapt their search.
Mm-hmm.
But the second related part, and what's really unique about this setup is, again, imagine that you have 10 cooks that try to do a meal in a room, and they can see what each other are doing, and they can maybe copy what each other are doing. If you had these 10 people in the same room, it would be really difficult for me as a scientist to track, is number 3 copying number 7, because he might be looking in that direction, but it's really difficult to trace people's behavior. Here we had an opportunity where we could 100% closely trace, is number 3 clicking on number 7 solution, clicking copying that, and then adapting that further. So we can really track people's behavior. And what we then saw was that people don't just do this adaptive search on their own solutions, but also if I am the second best, I'm still not the best. I'm the second best, your solution is the best. I copy yours, but since there's no point in submitting the exact same solution again, I do modifications, but again, I do small modifications. It's as if I'm in a mindset of, I'm doing good right now, let me just do some minor stuff. Well, if I'm way behind, I copy the same solution, I copy your solution, but then I will do a big change. So apparently people in this sort of collective setting engage in this kind of social learning. We as human beings, we don't just copy other people. It's like if I see a great recipe out there, I might sort of use it, but I'll adapt it.
So we're not pure we're not pure copy pasters. We just
we
adapt it always slightly, a little bit, and
exactly. We like to sort of, human beings, we have a tendency to like to sort of put our own angle on it. And how much we adapt apparently depends on where we're coming from. So we've copied the same solution, and then before we submit it, the changes we do, the extent of the changes we do, they depend on where we're coming from.
Yeah. So how well we did, or
how well we did before.
Yes.
So this of course changes over time, because if I was doing poorly, come up with a great solution, then I'm in a different place. Then I'm in a place where I do small modifications.
So, I know what we did in our lab. I know roughly how the Alice interface looks, but I don't know exactly the nitty-gritty details or thoughts that went into. So how did you, what design considerations are there now in this Alice interface, or Alice game, Alice challenge game?
Yeah, so the game, there were a couple of things that we really wanted to get right there, is that we already have a lot of studies that look into how an individual tries to optimize search. As I mentioned before, often some artificial problems. So we needed a game interface where people could clearly see what they did. They got point feedback, which they got from the actual physics experiment 35 seconds later. And then they could adapt their solution. So they got their former solution and they had to submit the next one, and they could manipulate that. But we also wanted to get to this collective search element. So there was also a leaderboard. So you could see in your group of 5, you could see who was currently the best one and who scored the most points, so to say, who had cooled down the most atoms. You could click on their solution, see what their solution looked like, and then further manipulate that. Yeah. So there was a lot of transparency, both in terms of what you yourself did, what the best current score was, but also how you could learn from that, click on that solution, and then manipulate that further. That really enabled us to, in a very detailed way, when we analyze the data, see how much do I change my solution depending on my feedback, depending on how well I do, but also how much do I change the solution of whoever I'm copying, whoever I'm sort of learning from. But it was all still in a controlled sense that I couldn't speak to anyone, I couldn't write, I couldn't ask questions. And we needed it still to be very controlled. We needed to be able to track exactly what information people had and what information people were responding to. So if I could have asked questions and someone else could have answered it, it would just have opened up a lot more uncertainty about what was actually going on. So that's how we ended up with this game design. It's very simple in some way. You have 3 lines that you should manipulate, and you have that information about others. So it's not the most enthusiastic game design maybe in the world, but it was clearly interesting enough for people to engage with and to keep them occupied for an hour, which was the extent of the experiment. So I mean, there are a number of things that I find really interesting to pursue. But one project that is fairly doable actually is that we have at ScienceAtHome this other project called Skill Lab, where we are trying to map the cognitive ability of Danes. So you can go to the website and then do a number of fairly short and simple games that we then can document, actually capture your working memory or your spatial reasoning or sort of similar fundamental cognitive abilities. And if we then maybe could link people's tendency to either just do very small adaptations in the Alice Challenge or doing big changes. I mean, we know that performance feedback plays a role, but maybe people are different. Maybe some people with a certain cognitive ability, I don't know, maybe the bigger the working memory, maybe the more you're able to think of different solutions in your mind and then do either smaller or bigger jumps. Mm-hmm. So right now in the Alice Challenge, in this paper here, we've shown a general tendency that human beings have. But of course, we also know as social scientists that we are different. You're different from me, and we have different personalities, we have different feelings, emotions, but we also have different fundamental skills.
Yes.
And maybe that difference actually then also plays out into how we solve problems. And that's a really interesting question that I'd be very curious to pursue in the future.
And then maybe combine the Alice Challenge. Again, run it again in a different way, and maybe then know who are the people.
Exactly. Have the same people that do the Alice Challenge also play the Skill Lab, and in total this wouldn't take a lot of time, and this would really be a substantial advancement for the kind of data that we have so far.